Let's have a look at the effect of forging on the microstructure. The forging can be cold forging, it can be hot forging. The process of the hot forging is you heat the material at a very high temperature until it's red hot. Then you actually put in some dye and apply the pressure, the forces, usually compression forces. In this case, the compression forces, or this thing is being compressed in the horizontal direction. Hence, the microstructure growth, you can actually see the growth or they are pressed, looks like they are pressed along the y-axis. Okay, now the grain flow is directional, and they are directed in the direction of where we apply the pressure. So grain flow is a directional orientation of metal grains and any non-metallic inclusion that have been formed because of the forging. Individual grains, they are elongated in a direction of the pressure, where we can actually see the plastic deformation or the permanent deformation as occur. Now the grain flow is the movement of the grain in the metal, occurs to some extent in all metal forming process and not only in casting. Now the properties of casting. It depends on the grain flow. Grains are the one who dictates the properties. Now the properties like the toughness, impact toughness, ductility, fatigue strength, and cracking, they can be improved if you have forged material, if you use the forging as the way of forming material. Now crack propagation, we can actually provide it a directional crack propagation. So in the diagram, if the crack is going to propagate in x-axis, it's very difficult. But if the crack wants to propagate along the y-axis, much easier. So we have given it a directional crack propagation properties. Now to get the maximum stress, to get the maximum properties, we can have the maximum principal axis aligned in the direction of the grain flow. And in that case, we will have the maximum UTS, ultimate tensile stress properties. Now let's look at the advantages of the forging. Forging can refine, reshape the grain structure. It's a lot better than the casting or the machining. And the grain structure aligns in a direction, it flows in a direction of the shape of the material. For example, you can actually see the grains is actually flowing along the shape. So it's quite give you a lot of superior qualities as compared to the casting. Casting have an isotropic grain structure, which may be strong in compression, but for other properties, tensile and the shear loading, it's not going to be as good as the forging. Now the structure reliability, because obviously you have forged in a specific direction, which means you have got properties which are superior in one dimension. So hence we can have a much better factor of safety in that forged component. Also, it can provide more uniform response to a heat treatment and the machining operation. Okay, next one, let's have a look at the rolling. Let's say we got an ingot, which is the casted metal out of the refinery. Now here you can actually see on the top the grain structure of very fast cooling, and then you can see the columnar grain, and you can see it's like kind of like a cylindrical, and the outer layers are that one, and the direction of cooling is from outer layer towards the inner layer where there is a line in the middle. Now if we let's say if we want to pass it to the rolling, There are two types of rolling: cold rolling and hot rolling. Hot rolling, we heat the material up to at least annealing temperature and we pass it through the roll. The speed of the roll, the pass of the roll, the difference between the one and the other roll is calculated, and we just put that one in. Now when you put that one in the wrought product with like larger grain structure, the grain structures are deformed and they are aligned in one direction. Sometime when you break the grain structures, there is a thermodynamically energy instability occurs, which means the new grain structures are going to form. And sometime, and it also because we are doing the hot rolling, the material is heated, so new grain structures are formed. And then the process, there's another process known as recrystallization process, which means that grain structures on the left sides is converted into new grain structures, which might be smaller, which might be different size than the initial. And this process is known as recrystallization process. Then there is a material structure which is known as material property, which is known as isotropic and anisotropic. Anisotropic properties are the properties that are directional dependent. If you apply the force, the materials might be strong in one way, but it's not strong in the other way. That's known as anisotropic properties. Sometime we need uniform properties throughout the material. So if there are grain structures which we don't want to be aligned in one specific direction, we want the grain structure to be recrystallized into smaller uniform grains, multiple grains, and the properties will be same all across. Sometime what we do is we just make the component out of the single crystal. So usually in turbines or mostly in application where the fatigue resistance is required, we use a material, we form the material by using a process known as single grain structure, and that gives us 100% uniform properties. If we have a look at the microstructure of the cold drawn steel, if this is an undrawn steel, we haven't put it through the rolling process. When we put it in the first one, you can actually see the tiny lines. These lines here are actually these lines here. You can actually see a teeny lines. These lines actually can define the direction of the rolling. Then this is the second pass. It's quite difficult to see what's happening in the second pass, but there is a line are in this direction. Yeah. So in third one, it is quite obvious. You can see the lines in that direction. So it's very obvious, the rolling lines. We can do the rolling, either a hot rolling or a cold rolling. Now, we are providing the energy. This will change the microstructure, which will change the properties. Now, the original undistorted structure will change into something else, or we will go back to recrystallization. So if you remember the previous slide, we discussed the recrystallization where you have the microstructure, you pass through the rolls, and the rolls elongated the crystals, and later on some new crystals are formed, and these new crystals are much smaller in sizes, and the new recrystallization happens, which will change, which will have a different properties. So the properties will be very much different at the start of the roll as compared to at the end of the roll. Now, effect of temperature on materials properties. Now, on the x-axis, you can see the temperature. On the y-axis, you can see the different properties: residual stresses, strength, hardness, ductility, and the grain size. So let's have a look at the grain size first. If you're doing the cold working, the grain size looks like that. This is recovery grain, this is recrystallization grain, and this is the grain growth. Because if the temperature is not decreasing, it's very slow cooling, that's what happened, the more grain growth. Now this is a bigger grain. The bigger grain will have less hardness, but it will have more ductility, and this is because of slow cooling, and it will have very less residual stresses. But if you have a look at the other side, if you have a look at this side, oops, sorry. If you have a look at that side, this is if the temperature is, cooling rate is very fast, yeah. So it's like, what will actually happen is the material will have a high kind of strength, the residual stresses will be a lot, the grain structure is going to look like this, and we need to perform a recovery process where we need to actually restructure the grains. Otherwise, the properties will be very poor. Now the next one. Thank you. Now we do a thing called homologous temperature range for the various process. That's the optimum temperature. For the cold working, the temperature ratio, the Tm is a melting point. It should be greater than 0.3%. This is the temperature range for cold working process. For a hot working, T over Tm, the working temperature over the melting temperature range, should be 0.6. For warm working, it should be between 0.3 to 0.5. When we perform the cold working, the products are stronger, but they are less ductile. The reason is because the microstructure is all distorted, and then they provide the resistance to the movement of the dislocation, which is deformation. Hot roll products are less strong, but they are more ductile. Now, the next one, the effects of machining on the structure. When we perform the machining operation, we need to actually calculate the speed of the tool. We need to calculate the angle of the tool, like how to perform that thing. And we need to find out how much mass is removed from the surface area. So it's not straight away process. If you change these variables, because every time the tool touches the surface, now the top one is the material removed, what will actually happen, it will increase the temperature of the workpiece. If the temperature of the workpiece is increased, the properties will be different, because that might enter into a single phase region, and then it will cool under normal air, hence normalization, which will give you different properties. The machining affects the surface, and as a result do not alter the macro properties of the material, but micro properties will be changed. Any residual stresses present on the machine surface can be removed by performing stress relieving heat treatments. Now, this gives you the kind of an idea about the different microstructure. If you have a look at that one, forging microstructure, all the grains are aligned in a proper order. This improves the ductility, toughness, and the fatigue resistance. Casting, they do not have any desired grain structure. If you have a look at the machining, the grain structure is properly aligned, unidirectional grain flow. That material means it's more liable to the fatigue, and they are more sensitive to the stress corrosion cracking. Stress corrosion cracking is a corrosion that happens under the applied stress condition. It can be tensile or it can be compressive stress.